For this project, we use uncooked spaghetti to fabricate a bar with an equilateral triangle cross-section. The required dimensions were 30 cm length and also 1.5 cm in thickness. To fabricate the model, we first arrange the spaghetti strands carefully into an equilateral triangle shape. We use adhesive tape as our mold to hold the spaghetti together and maintain the triangular shape during the fabrication process. The tape help to prevent the spaghetti from moving or prevent the spaghetti from misaligned while we assemble the model. After that, we check the dimensions to make sure that the bar met the required specification. The completed model was then ready for a bending test. Using tape as the mold was a simple and practical method because it kept the spaghetti from moving, kept it in the right position, and also maintained the shape and made the fabrication process easier and also more stable.
So next we'll be testing 2 kilograms of water on our triangle. The beam successfully holds 2 kilograms of water. So now we're testing for 5 kilograms on our triangular beam. It could successfully hold 5 kilograms of water. This 5 kilograms, we can hear the structure breaking, right?
This is our 9 kilograms of water. We're going to test it on our beam.
As we can see, the limit for our triangular beam is 9 kilograms of weight.
In the real experiment, the beam simply rests on 2 tabletops that only provide upward support. However, in engineering analysis, we model this as a simply supported beam with 1 pin and 1 roller. The standard idealized model provides 3 unknown reactions that perfectly match our 3 equilibrium equations, making the structure statically determinate and solvable. Since our applied weight acts entirely vertically, the roller's ability to move horizontally never actually comes into play, meaning this ideal model perfectly mirrors our real-world experiment while keeping the math straightforward. First, I will explain the 2 kg load analysis. The applied load is 19.62 Newton, which is calculated by multiplying 2 kg with the gravitational acceleration of 9.81 meter per second square. From the equilibrium equations, both support reactions at point A and point C are 9.81 Newton upward, showing that the beam is symmetrically loaded. Next, I drew the shear force diagram. The shear force starts at positive 9.81 Newton, drops to negative 9.81 Newton after the load, and finally returns to 0 at the end of the beam. For the bending moment diagram, the maximum bending moment is 1.47 Newton meter, which occurs at the center where the load is applied. This is the highest bending stress experienced by the beam. Next is the 5 kg load. The applied force is 49.05 Newton after converting the mass into force. Using static equilibrium, the reaction forces at both supports are 24.525 Newton upward because the load is applied at the center. The shear force diagram follows the same pattern as the 2 kg case, but with larger values. The shear force changes from positive 24.525 Newton to negative 24.525 Newton. The maximum bending moment increases to approximately 3.68 Newton meter. This shows that increasing the load also increases the bending moment acting on the beam. Finally, for the 9 kg load, the applied force is 88.29 Newton. The support actions are equal at 44.145 Newton upward due to the symmetrical loading. The shear force diagram changes from positive 44.145 Newton to negative 44.145 Newton before it returned to zero. The maximum bending moment is approximately 6.62 Newton meter, which is the highest among all three loading conditions. This indicates that as the applied load increases, both the shear force and bending moment are increased proportionally, resulting in greater stress on the beam.
In conclusion, all the project objectives were successfully achieved. We applied the principle of mechanics of materials by designing and fabricating a spaghetti bar with an equilateral triangle cross-section. From the structural analysis, the maximum bending moment was 6.62 Newton meter and the maximum shear force was 44.145 Newton. During the experiment, the spaghetti bar successfully support a maximum load of 9 kg, which is 88.29 Newton before failure. This shows that the equilateral triangle cross-section provides good structural stability and distributes the load effectively. Overall, this project improved our understanding of bending behavior, structural analysis, and practical engineering skills such as fabrication, teamwork, and problem solving. That's all from us. Thank you.